Hey, this is Bill. Today we're starting Chapter 3 of our CompT and Network Plus class. Remember, this is based off the book from Mike Myers, McGraw-Hill Publishing, Managing and Troubleshooting Networks, 5th edition, exam N10-007. So Chapter 3 is largely Ethernet basics. This is a classic Ethernet. We're talking 10, maybe 100 meg Ethernet. Just a real quick history. Ethernet was developed by Xerox in 1973. The technology at that time was based on the maximum bandwidth of 3 megabits per second. In 1979, Xerox partnered with both Intel and Digital Equipment Corp to develop DIX Ethernet. This was a 10 megabits per second network based on a bus technology. This consortium, after they developed this technology, the specification, gave the spec to the IEEE to form an open standard. The IEEE formed an 802.3 committee to manage the Ethernet specification. Over the years, the IEEE has expanded the specification well beyond Ethernet, that original 10 megabit Ethernet. And we'll cover that a lot more in Chapter 4. Remember the Ethernet frame from Chapter 1? This is a 1,518 byte frame where we have the destination MAC address, source MAC, the type, the data, and our frame check sequence, which is used for error detection. So how does our network card know when this Ethernet frame starts? We do this with a preamble. The preamble is 56 bits of alternating ones and zeros, followed by an 8-bit starter frame delimiter. And it looks just like we have below. So when your network card sees this pattern, it knows the bit immediately following this is going to be the first bit of our Ethernet frame. And again, our Ethernet structure, we have a destination MAC address of 48 bits. This tells us where the frame is destined for, who's going to receive this frame. Our source MAC address, which is 48 bits, again, who sent the frame. Our type, which tells us what kind of data to expect. And here are some common types. This is a hex value, but it is, keep in mind, just 2 bytes long. So 0x, whenever you see 0x, that denotes it's a hex value that follows. So 0x800 is an IPv4 frame. We'll discuss more about IPv4 when we talk about layer 3 in a couple chapters. 806 is an ARP, or Address Resolution Protocol. Again, we'll discuss that in a future chapter. 88CC is the Link Layer Discovery Protocol, and 86DD is IPv6, and we'll cover IPv6 later in the book. Our data is going to be a minimum of 64 bytes long and a maximum of 1,436 bytes. If for some reason the data does not equal 64 bytes, there will the network interface card will add padding to make the 64 bytes. And then we have a frame check sequence, which is used to detect errors in transmission, and that is 4 bytes long. Ethernet networks have a naming standard. This naming standard gives us an idea of the bandwidth supported by the Ethernet, along with the type of cable used, or the length in the old specifications in classic Ethernet. So it starts off with a number, we'll say 10 or 100 or 1000. That's the bandwidth of our network. So a 10 would be 10 megabits, and that number is in megabits. So 10 is 10 megabits per second, 100 megabits, 1000 is 1 gigabit or 1000 megabits per second, and then of course 10,000, which is 10 gigabit, 10,000 megabits. For this class, everything is baseband, so it's 10 base, and then we have some nomenclature after that. If it starts with a number, it'll be either a 5 or a 2. The 5 is our first standard. That was coaxial cable, and that was 500 meters length of coaxial cable. If it's 2, that's also coaxial cable, and that stands for 185 meters, maximum length from end to end of that cable. T is unshielded twisted pair, and that is 100 megabits. This is going to be a physical star, so it's 100 megabits from, say, a workstation to the central hub or the central switch. If you see it, if the name nomenclature ends in a TX, that's twisted pair cabling using 2 of the 4 pairs in the network in a UTP cable, and that's typically used in 100 megabits, 100 base TX. Again, we're still talking 100 meters of distance from the compute device, or the end device could be a printer, thermostat, computer, all the way back to your central hub or switch. T4, this is an old standard. We really don't see this much anymore. This is twisted pair cabling using all 4 pairs of cable. FX is fiber optic cable. It's the first fiber optic standard we had. In Ethernet, it's 100 megabits baseband and fiber optics. If it ends in L, S, or C, these are different fiber optic options that we have. So using this, a 10 base 2 network is 10 megabits per second, 185 meters long in baseband. 10 base T is 10 megabits per second, baseband over twisted pair cable. And 100 base FX is 100 megabits per second over fiber optic cable. Prior to 1990, Ethernet networks were run on coaxial cable. In 1990, the IEEE came out with the standard for twisted pair cable, and that was the 10 base T standard. Along with the twisted pair cabling piece, the IEEE defined a hub, which gave us the logical bus and a physical star. Within our Ethernet networks, UTP cables, unshielded twisted pair, must be category 3 or better. Pins 1 and 2 in the cable are used to transmit data. Pins 3 and 6 are used to receive. We still terminate pins 4, 5, 7, and 8. The UTP cable terminates in an RJ45 jack or a Mod 8 connector. In half duplex mode, only one device in the network can transmit at a time. The UTP termination standards are defined by the Telecommunications Industry Association and the Electronics Industries Alliance, or the TIA-EIA. Here are 2 devices that you'll need to know about in your networking career. One is a crimper. This is used to terminate a patch cable. Put the modular 8 jack on that patch cable, and that will be plugged into a device like a PC or a wall jack. And a punch tool, we use these to secure our UTP cable to wall jacks and patch panels. Here's a wall jack on the top and a patch panel on the bottom. Wall jacks, that we're plugging in a single device here. These might come in bundles of 2 or even 4, and again, if they do come in a bundle, I'll say 4, that's going to be 4 unshielded twisted pair cables. Each cable is going to have 8 wires in it. And we have a patch panel here, which these typically come in 12, 24, 48 port designs. And you get a front and a back. The front looks like an RJ45 port, Mod 8 port, and the back is where we terminate our cable with a punch down tool. Two different specifications, the 568A or the 568B. These are not compatible with each other, so you have to pick one or the other in your network. This means if you go with the 568A network, you want your wall jacks to be 568A and your patch panels to be 568A. Do not put a 568A wall jack with a 568B patch panel. You end up creating crossover cables. So you want to keep them 568A wall jacks, 568A patch panels, or a 568B wall jack with a 568B patch panel. And you'll see here to the right the color pin differences. It is important for the exam that you memorize these pin differences. This is a fair question, and it's also fair in the industry to ask when someone hands you a patch cable to build or to verify, to know what these patch cable colors are. So in the TIA EIA 568A, pin 1 is green-white, pin 2 is green, pin 3 is orange-white, 4 is blue, 5 is blue-white, 6 is orange, 7 is brown-white, and 8 is brown. For the TIA EIA 568B specification, pin 1 is orange-white, pin 2 is orange, pin 3 is green-white, pin 4 is blue, pin 5 is blue-white, pin 6 is green, pin 7 is brown-white, and pin 8 is brown. So we're really just swapping out the green, the white-green, the white-orange, and the orange cables. To run Ethernet over fiber optics, we have the 10 base FL specification. This is a 10 megabits per second bandwidth, again baseband network, over fiber optic cable. The maximum distance we can run this fiber optic cable is 2 kilometers. It uses multi-mode cable, multi-mode fiber optic cable. Again, it's a physical star, but a logical bus. Remember some facts about fiber optic cable? It's immune to EMI. Keep that in mind. Fiber optic cable is the only cable immune to EMI. The cable is very difficult to tap. There are 2 types of fiber optic cables, single mode and multi-mode, and we have various termination types. We have SC, ST, and LC. Now, one thing about Ethernet networks, as the number of devices increase, the number of collisions increase, and it grows quite dramatically. This is a feature of all half-duplex networks. You do not need a hub to have this chart look like this. Any sufficiently large half-duplex networks will work. So it could be a hub, it could be a coaxial cable, any number of things that could cause these collisions. In our traditional Ethernet, remember we were on a bus network or with the hub, and everything was half duplex. So with this half duplex network, the more devices we added to our network, the greater the number of collisions, and it rose quite dramatically. In the first Ethernet networks we had, our coaxial-based bus networks, we tried to keep the number of devices on the network down to about 30, maybe 35. In the hubs, there is a specification that supports up to, I think, 1,024 port hub. You'll never see more than probably 35 or 40 on a classic hub. And that was a really, really busy network. What is a collision? A network collision occurs when 2 network devices transmit that share the same medium, so a hub or a coaxial cable, send data at the same time. When the Ethernet frames meet, they cause a collision. So a collision is bad. In low numbers, no. We expect collisions on our half-duplex Ethernet networks, but we do have to manage them. If you get in high numbers, collisions can actually cause problems with network performance. So how do we manage these collisions? We use a process called carrier sense multiple access collision detection, or CSMA-CD. We use this process to manage our collisions. So how does this work? Kind of have this flow chart. So we have a device that wants to transmit. So it must sense the network. This is carrier sense. When we talk about sensing the network, it's actually asking the question, is there any traffic on the network? If it listens and does not see traffic, the system can send its frame. If it sees traffic, it just kind of holds off and waits until it doesn't detect traffic any longer. But we'll say at this point our device doesn't sense traffic, so it transmits its frame. Well, after the device is finished transmitting its frame, the device will listen for a collision. And it listens for a certain specified period of time, just several milliseconds. If the device senses a collision, the devices that all sensed the collision, that all transmitted, will send out a jam signal. This jam signal tells all the systems on the network, there's a problem, please back off and don't send data. For the systems that caused the jam, they will wait a random period of time, they call it the back off period, and they will begin this whole process over again. If a collision did not happen, the data finishes transmitting, and the device that transmitted the data goes back to the process of deciding, does it have traffic to transmit? If the answer is yes, it does this whole process again. If the answer is no, it just whatever mechanism is used to queue up data in that system to send traffic, that process will happen. In Ethernet, we have a term called a collision domain. A collision domain is a group of Ethernet devices that can send data. They can all send data at the same time and cause collisions. This is unique to half-duplex Ethernet. On a coaxial cable, on a hub, or half-duplex session connected to a switch. Keep in mind, if the device on the switch is half-duplex, collisions can occur. If it's a full duplex, collisions don't occur. Hubs are layer 1 devices that forward and repeat all frames to all ports except for the one that was the incoming port, creating a single collision domain. So in our hub, if we'll say we have a 12-port hub, on port 1 we have a device that transmits. When that frame hits the hub, it's going to be forward and out frames 2, 3, 4, all the way through port 12. So how do we eliminate or reduce collisions? Well, we have to install a layer 2 device. So the first layer 2 devices were bridges. The new layer 2 devices are switches. So you install these layer 2 devices, and they can start to help isolate some of these collisions. In a switch, each switch port is its own collision domain. So if you have a 48-port switch port, it's got 48 collision domains. If you have a 48-port hub, it's a single collision domain. Now, switches can support simultaneous conversations. So switches can operate in what's called full duplex. When we turn on full duplex, we turn off the CSMA-CD. So this process here gets turned off in full duplex. So if we have a switch and all of our ports in that switch are in full duplex, we've eliminated our collision domains, because collisions can't occur in full duplex. So with the switch, we have a source address table. Cisco calls it a content addressable memory table, or CAM table. A switch is used to manage and forward frames. So a switch actually builds this switch address table in memory, and the way this works is as a device transmits, we'll say In this scenario on Ethernet switch 1, device A transmits. Device A is connected to port 1. The switch will notice that MAC address of A is on port 1, so it will put the MAC address A on port 1. When B transmits, it puts B on port 2 of Ethernet switch 1, the MAC address of the device B, and C goes on port 3. This switch connects to two other switches, so when switch 2 transmits, switch 1 will know that switch 2 is on port 4, and switch 3 is on port 5. A very similar process takes place on switch 2 and switch 3. Just they're a little bit different. So study how those work, how these look, and you'll get an idea what that source address table looks like. Continuing on with that source address table, as devices are transmitted, as frames are forwarded, we'll get more and more built up on the table, including what ports plug in or what switches and what devices are on other switches. So switches are intelligent, and I've gone over how they will determine what MAC addresses exist for devices that plug directly into them. Like, for example, Ethernet switch 1 has computers A, B, and C plugged in, so it knows A is on port 1, B is on port 2, and C is on port 3. When Ethernet switch 2 transmits data of some sort, could be a broadcast, could be a request for some kind of information, could be an SNMP packet, switch 1 will know that switch 2 is on its port 4. Same thing with switch 3. Ethernet switch 1 will say, oh, switch 3 is plugged into port 5. On switch 3 we have three other devices, a workstation G on port 1, server H on port 2, and server I on port 3. So as these devices are communicating to other devices not on Ethernet switch 3, the CAM table or the SAT table on Ethernet switch 1 will figure out where G, H, and I are located, and they're located off of port 5 on its switch. And then on switch 2, we have devices D, E, and F that's also connected to switch 1. Switch 2 is connected to switch 1 on port 4. So you'll notice that switch 2 on port 4 has computers D, E, and F. On port 5, it has switch 3 along with G, H, and I. And we build up something very similar for a static address table on switch 3 and on switch 2. Now what happens if we decide we want to make a loop in our network to add redundancy? So we connect switch 3 to switch 2. Notice now it looks like we have a redundant network. So on Ethernet switch 1, we have on port 1 we have A, on port 2 we have B, and port 3 we have C. On port 4 we can see switch 2, and switch 2 has plugged into it D, E, and F. But you know what? I can also see switch 3 through that port because it's connected to Ethernet switch 2. And I can see G, H, and I on that one. And then you know what? Switch 3 connects to switch 1 in that roundabout sort of way. And I can also see switch A, B, and C on port 4. And on port 5, I can see switch 3 along with G, H, and I. I can see switch 2 with D, E, and F on it. And A, B, and C also can be seen. And the same process happens on switch 3 and on switch 2. This is called a loop, and this is bad because we'll say device A wants to communicate with device D. You can see D on both ports 4 and 5. How's that going to work? To manage that bridge loop, we have a protocol called spanning tree protocol. Remember, bridge loops only occur at layer 2. Layer 1 does not have loops. Layer 2 has bridge loops. We manage these bridge loops with our spanning tree protocol, or STP. Spanning tree protocol uses bridge protocol data units to manage the setup and the overall protocol, the overall spanning tree protocol. When we do in the process of creating this, spanning tree creates a root bridge, or elects a root bridge, identifies designated ports, and the cost to the root bridge. Spanning tree protocol actually prevents bridge loops. At the process, when our switches first boot up, it puts all the ports into a blocking mode. In blocking mode, no traffic except for the BPDU can transmit. Every 2 seconds, the BPDU is broadcast. That BPDU, for the selection process, will contain the MAC address of each switch. The switch with the lowest MAC address becomes the root bridge, or the root switch. Once the election takes place, all the ports in the root bridge are identified as designated ports. The other switches that connect to the root bridge, the ports that are closest to the root bridge, are designated as root ports. Then to prevent the actual loop, one of the ports furthest from the root bridge is put into a blocking mode. The blocking port will not allow any traffic to pass except for BPDUs, or bridge protocol data units. A spanning tree has the following port states. Disabled. This is an administrative function where whoever the administrator is of that switch actually designate the port as down. There's no traffic passing on that port, not even BPDUs. Blocking. In a blocking state, this occurs when the switch first boots up, or for the switch port that's furthest from the root bridge, and it put no traffic will pass that blocking state, that blocking port, except for BPDUs. Listening. When a port's in listening mode, it flushes the MAC addresses from memory. It waits 15 seconds and then goes into a learning state. In a learning state, the switch learns MAC addresses and what MAC addresses are connected to which ports. We stay in the learning state for 15 seconds. And then forwarding, we will go into the forwarding state when we start to send and retrieve data for normal network operations. When our network topology changes, devices have to learn the new configuration, and when that configuration completes, the BPDU, the sent, is called a topology change notification, or TCN. This whole process can take about 50 seconds for this blocking, listening, learning, forwarding process to occur. Now, ports that support computing devices on your switch, so ports that have printers and workstations and thermostats and access control units and whatever, those devices should be in what's called port fast mode. They will not participate in spanning tree. Our spanning tree is defined by the IEEE as the 802.1d specification. There is a newer specification called rapid spanning tree, and this can replace the 802.1d specification with 802.1w. Rapid spanning tree converges in about 6 seconds versus 50 seconds for spanning tree. And that is it for chapter 3. The important thing here to remember is the nomenclature, the naming of our networks. Remember, we have the number 10 or 100, that's the megabits per second of bandwidth we have available. All of our networks for this test are going to be baseband, and then our designation after the base. So if it's a number, it'll be either 2 or a 5. 5 is 500 meters. 2 is 185 meters. That's the length of our coaxial cable. T is twisted pair. Then we had F, L, and S for fiber optics. So remember those, and you'll understand, you'll be able to identify Ethernet networks and how their bandwidth is associated with them. We also discussed the CSMA CD process, or carrier sense multiple access collision detection process. That occurs only in half duplex Ethernet. And then we discussed spanning tree. So our spanning tree protocol and how that worked. Remember, spanning tree is the one protocol we use to prevent bridge loops.